example, I claim gradient is a one form. What do I mean by that? Or gradient of some function f. Okay? Let's imagine our function f lives on our manifold. Okay, and there's something we often write, which is df. So this is sort of calculus notation. You might write df is df dx, or let's do all of them. dt plus df dx plus df dy plus df dz. This is something you would write. This is sometimes even called like a theorem in calculus, but it's more like a definition of what they mean by this little d. So this is a very natural equation. And notice there's no minus sign here, right? That's why this is not going to involve a metric. There's no like hint of the Minkowski -1 time and space being treated differently. This is just the gradient of some function of 4 variables, okay? And so normally you would think of this in vector calculus as some kind of dot product between the gradient vector, whose components are df dt, df dx, and the displacement vector or something whose components are dat, dx, dy. This should say y. The computer is struggling. Normally you would think of it as a dot product between vectors, but we don't want to do that because we're going to use dot products for lengths. And lengths in space-time intervals are going to have this -1 here, and there is no -1 here. Okay? So this is really not to be thought of as a vector product. It's to be thought of as df dx mu dx mu. That's just our notation, summation convention, right? But we're going to identify these little dx mu's as just another notation for our basis 1 forms. So it's going to be df dx mu theta hat mu. Okay? This is just notation. Okay, I could have written theta hat mu at the beginning as representative of a little displacement or something. And so we're going to continue with this construction, and we'll regard the components. Oh. Okay, so we have this equation that says df, I'm just going to write it again, df, which is going to be our abstract 1 form, is given by this thing, df dx mu, which prior you would think of as the components of a vector, but here they're the components of the 1 form. And then they're multiplied by these coordinate basis elements, theta hat mu, basis 1 forms. And why is this useful? Well, we might want to ask a question like, how fast does f change in some direction? Or maybe how fast does f change along a curve? Let's do it that way. So suppose we were asking, how fast does f change along a curve x mu of lambda? Okay, so normally the way we would do that is we would just take the lambda derivative, right? D by d lambda of f, and just evaluated it at x mu of lambda, right? That would be the answer to that question. But let's see how this can be expressed in terms of our construction of the 1 form as a gradient, construction of the gradient as a 1 form. So let's start writing this out by the chain rule. This is going to be df dx mu dx mu d lambda. That is just the chain rule from ordinary calculus. Okay, there's a sum over x mu. Now let's see if people are making connections. This came up before. We gave this a name. Anyone remember this piece here? Sorry? V, yeah, it was the tangent vector. These were the components of tangent vector. Okay? Now these gave a name over here. These are the components of the one-form df. So the abstract one-form df has downstairs components of one-form. Okay? So the answer for this was actually just the one-form abstractly acting on the tangent vector t abstractly. Okay, so the one form is a machine. The gradient of f is a machine. It takes a vector and it answers the question for you: how fast is the function that you took the gradient of changing in the direction of that vector? One sec. And that's why it's a one form, not a vector, because it asks questions. The vector represents the direction. The gradient answers the question, how fast does this function change in that direction? And that question involves plus signs, right? It involves plus signs here, not minus signs. You can't have the metric involved. That's why it's not a vector. It's a one form. The one form is the thing that lets you sum things up without minus signs. Just sum them up, as Evan was pointing out. Wolfgang, you had a question?
So this is related to the tangent, which I am kind of forgetting how we defined them earlier. Did we ever parameterize it with lambda?
Yeah, we started with the curve f mu of lambda. The tangent is parameter dependent.
Okay.
So if you change the parameter, the length changes. We'll get more into that when we do the physics, yeah. But when you have a parameterized curve. So that's a good point. I probably should have mentioned that when I defined it.
So this kind of has a t of lambda buried in it that we're just right now.
Yes, how fast does a parameterized change along a parameterized curve x? The question has a lambda in it, and so does the answer.
Okay.
And the lambda dependence is in t. Good question. Yes. Your Kush?
Yeah.
Yes.
While we applying the chain rule, why didn't we take the partial derivative out, like the constant? Just applied,
Partial derivative what?
like we took partial derivative of f with respect to x mu
Yeah.
as out. Like we didn't apply d lambda to it. We just applied d lambda to dx.
D lambda I haven't even written.
Like in the denominator.
Well, that's a derivative, d by d lambda.
Yeah, yeah. So I'm saying that derivative didn't act on the partial d over.
No, it doesn't know how. D by d lambda is just an ordinary derivative. The only thing it can act on is a function of lambda. So the only thing it can act on is x mu of lambda. That's sort of how the chain rule works, although it's often buried in the notation. Vivian.
So what distinguishes a one form from a vector is a one form is an operator,
Mm-hmm.
and that it adds up all the components, whereas the vector,
Well, the one form, when given a vector, adds up the components. Its components get dotted in, if you like, with the components of the vector. It needs a vector, yeah.
yes. Whereas a vector, like you're comparing it to the metric.
I haven't even introduced the metric. I'm just saying that in the past, when you've written things out as dot product-like things between vectors, there's secretly been a metric there. And we will do that soon enough, but for now there's no metric, and the adding up together is always one forms acting on vectors. Yes?
You were saying something about in here how there's kind of the gradient tells you how it changes along some distance, or like this is basically what we're doing here.
Mm-hmm.
Where does the notion of the distance come from? Because you talked
I shouldn't really have said distance if I did. I don't think I did, but if I did, I shouldn't have. Right now, it's all this function x mu of lambda. That thing someone provided tells you how fast you move along the manifold, if you like, along the space. It's just you give me a lambda and I give you an x. You give me, lambda plus 1, I give you a new x. That defines it. And if you want to know how does f change along x, the relevant thing to do is take the lambda derivative. The physics of that depends on what lambda is, but abstractly, the relevant only way to ask the question mathematically, how does the f change along the curve, is df d lambda. I'm just showing how the gradient relates that. Yeah?
One comment to the question. I think distance included in lambda.
There's no metric yet, so there's no distance.
Yes, but normally one will think of it like that.
If you choose lambda to be distance, then it can be distance. If you choose it to be time, then it can be time. You know, yeah. Okay, good. So the math went pretty slow, but the conceptual stuff is very important. So I'm happy with the pace.